so we might as well.
Yeah, we are on.
Oh, nice. Okay. Okay, so what do you want to cover today, Rajan? You had some.
Yeah. So yeah, two important topics. One of them is the from the last time we talked about the dimensions, right?
Yeah.
So the dimension of space and time. The second one is about gravity and the Bernoulli effect.
Okay, so, I think we should have this probably as some sort of let's keep it as kind of maybe more conversational because no one has a presentation or anything.
Yeah.
So allow back and forth.
Yeah.
But we'll stick also another kind of ground rule I was thinking of is that we would have, instead of like someone, have you heard of this phrase gish galloping? Do you know what that is?
Interrupting?
No. Gish galloping is where it's usually to do with debates and argumentation, but where someone will they'll just keep talking and move.
Yeah.
Well, wait. I haven't finished yet. They'll move from point to point. So like, yeah. So what I'm trying to say is like, if you're going to say something, make sure, and this is not directed at you or anyone in particular, just in general, make sure you have a point that you were trying to say and then deliver that point. Now, if the argument you're making encompasses lots of different points, that's perfectly fine. But the issue would be not to move from like one point to another just in a chain, I don't. So that's not any. That wouldn't be. That's something to bring up maybe in an email or something. But yeah, this doesn't really need to be stated here. Okay, so yeah, so let's keep. So I'm basically saying we'll try and stick to a point and then move on to another point later on. Then when we're done. Right. That's it.
Okay. One thing we can do is like we give a couple of minutes to each other. Like I talk about a couple of minutes or so, and then I stop. And then you.
Yeah. Yes. We'll have like a kind of a discussion kind of thing. Okay, that sounds good to me. Okay, so what was the other one you were looking at? So the first one is dimensions and time. Is that right?
Yeah, dimensions and space and time. Dimensions of space and time.
Okay, and the second issue you wanted to bring up was?
Gravity and the Bernoulli effect.
Okay, so when talking about the time thing, myself and yourself and Christian, when we're kind of delving into Christian's, how would you say, like geometry of space and subspaces?
Yeah.
And I noticed there's a good few problems with it, but I mean, I don't know if we should discuss that with Christian not here. Yeah, what do you think?
Yeah. We can kind of touch upon this, and when Christian comes, again, the rule for Christian also, the 2 minutes will apply so that, we get, for everybody.
Absolutely.
Gerd doesn't talk much. To
be fair, it's kind of Christian that I'm thinking of, because Christian's very good at doing these long monologues that go on for about, I don't know. So yeah, we just need to be focused on the specific thing that we're talking about and then move on to the next one.
Yeah.
So, yeah. Okay, so we can discuss, I think it's fair to discuss Christian's work, like,
yeah.
Like in just general terms, like we would anyone else's work. So,
yeah.
So the thing that I'd said to him previously is that it seems like the mathematics side, the equations and all on Mathematica, that side of the work is highly developed. But the criticism I had is that his other sort of, I suppose, his interpretation of the model with this 6-dimensional manifold and what else does he have? It's even up to 10 dimensions. I just don't think that's well enough developed. And I said that to him last week, I think, or one of the weeks, and he kind of, I think he gave me a paper to read, but it doesn't really go into that. And I haven't collected my thoughts on this issue really that well, but what I noticed was that some of the claims he's making about, for instance, this, so he has these pixels, yeah, which are kind of cubes, and then he's facing the sides by bending it into a donut and then bending that into another donut. And then finally, he says you need 6 dimensions to do it because there's no way to bend the inside to the outside. So the point I'm making is that his equations are highly developed, but they don't extend into this geometric realm. You know, so we'd expect to see either equations to, how do you say, to like as evidence of what he's claiming with the 6-dimensional warping, and or we'd need visuals, but actually no, you need both. So you need equations and possibly visuals just to help to understand. So I think that his point is wrong because, as he said, so I was showing that if you were to extend the cube to infinity and then join it at the projection point around a sphere, then you create a torus. That's fine. I think his objection was that you're not meant to extend it to infinity. But here's my rebuttal to that. Let's say we didn't extend it to infinity. We just wrap it around in a finite area. And we stop before they touch, yeah? And then you take the other 2 sides and then you wrap those around. And you stop before those touch. Now you have a sphere with a square hole in the top, kind of a cube-shaped hole, really, but with no tops and no bottoms. Now your next step is to efface, or yeah, to glue the inside to the outside. Now note, we haven't glued any sides of the cube together yet, but we will in a minute. So, but to do that, you can take the inside of the sphere and bring it up so that it matches the inside of becomes another side of this cube that we're forming. And then the outside would have to balloon out and come back around and then sit on the top and completely close the cube. Now, in order for that last transformation to happen, that will fill all of space infinitely. So no matter what way you do that, it's still going to fill all of 3D space infinitely. So that's why it's perfectly valid to just stretch the cube to infinity in all directions. But we still haven't finished the final thing. Now we have, instead of a cube filled with energy, we have all of space filled with energy and a cube that has nothing in it. Yes. And then so what we want to get is the left-hand side of the cube is joined with the right, and the top with the bottom, and the front with the back. So to do that, now we have like a negative space cube. We just shrink that cube together to a point, and now all the points in the cube are united. So that's how you do it. And that, in order to to stretch the outside so that it comes up to the top, I'm pretty sure you can just do that with normal, like 3D maths. I don't know how you do that, but a way you can, I would say that it's very possible in 4D. And actually, what I'm describing here is just the simplest way of describing it that anyone could understand. But if you're going to actually do this in reality, you'd probably just use a 4D transformation on the stereographic projection hypersphere, 4D hypersphere. And that would be that. And that would be the easiest way to do it. So that's what I propose. So basically, the end point I'm trying to make is that you need 4 dimensions to do this. And what I feel is that he didn't make the argument that 6 dimensions are needed. And in fact, his argument that he's making it's contrary to what we know about spatial dimensions. In fact, he's arguing that how we describe spatial dimensions as having, that they're all orthogonal to one another is incorrect. So, but at the same time, he's trying to apply that to 6-dimensional Calabi-Yau spaces used in string theory and such, but those are rooted in orthogonal dimensions. So there's an issue there. So I would, yeah, so basically, that is the main contention I have. But then we have to go back and look at his mathematical work and say, well, then his interpretations of what is going on in the equations have to be incorrect because his logic is incorrect from a geometric point of view. So then this raises the question, is all of his work incorrect? Or that can't be the case though, because he's getting proper answers. So it's just the geometric interpretation. But then, sorry, the real question we have to ask then is, can the unique hyperspheric model be used to plug the gaps? And therefore we could find a unified model where his equations work with the unique hyperspheric model to produce something that's, you know, really understandable and very based in physical reality. Now that would be a very good outcome, but I think it will take some effort, I think, to get Christian to come over to my side and see that. What do you think? Rajan, you still with us?
Yeah. Oh, yeah. So what I was thinking is that also to make it, I think, so we can, you know, we can give 5 to, you know, about 2 to 10 minutes for each person, right? And at that time, everybody else mutes, like I was muting when you're talking. Yeah. That's a good idea. Then after that, you are already prompting, you know, what you think or something. At that time, I switch back on. Then I give a 5.
Yeah, sorry. What I'm trying to say is, you know, just a sort of we can have a conversation. You don't. Yeah. I mean, if you want to be that controlled about it, that's okay with me. But you know, I'm not imposing that kind of limitation on anyone. But yeah, I'm just saying, you know, like deliver what you have to say, and then we can have like have a conversation, a back and forth about it. But
yeah.
Okay.
So you know, each person gets like 2 minutes to 10 minutes, because to make a complete point, you know,
okay,
so without interruption,
yeah,
you know.
I agree actually, because like when I was talking there, I thought I was just going to say a few sentences, but it actually does take a while to express yourself. So
So yeah, so I want to give you that time without, you know, without interrupting. So what I was trying to say is that I believe in your geometry space. I give it to you because you have done a lot of work. At 288 cells that I have not completely gone through it, but I like it, so I want to go through. That's why I wanted to think. I think it's a good way to you know, really authenticate, you know, the understanding of geometry. I think you have better understanding of the space geometry, and you know, than me, and I have good. I think I have fairly good understanding of the topology of time. So I think what is happening is, what you mentioned is a very good, excellent point about Christian. I think it's a confusion between space and time. Like Einstein also went through the same problem, Gaussian transform, things like that. But for Christian, it's iSpace. So he thinks that there is no real time, it's only space, and the space creates time. You know, I think that's part of the problem, that he's getting confused. And I think we have to separate the two. I agree with you. Like you said, geometry of space, I was thinking clearly, when you talk about space, you concentrate on that. Geometry of space starts with Euclidean, and then you have to argue why it goes to 4 dimensions. I think you have a good argument about the cube being 4. I don't understand completely, but I understand conceptually how the cube, when it folds back, it becomes like continuum, like a toroidal thing. And I can deal with that. Actually, I was thinking the same line, that actually there's only 4D space, but 6D time. And I will tell you that so geometry of space is 4D, like toroidal or something like that, like you mentioned, or hypersphere. But topology of time is Kalibu-Yau. So Kalibu-Yau manifold is actually time, it's not space. I will tell you what those times are. I already put 4-vector time called local time, proper time, then real time, and global time. But there's 2 more times called quantum time and also astrophysical time. So they constitute the six-fold dimension of time. Okay. So what's happening with that time is that the time is created if the body is not there, like a particle. When the particle is forming, for example, for superluminal thing, that's why I believe with Emmanouil that there's a multi-phase. So there's a superluminal phase where there's no particular topology, there's no particular geometry or anything. But from that, either through hot PDP mechanism, something like that, it forms particles. And when the particles form, it forms an interface called vacuum. And the vacuum holds the speed of light constant. So that for a particle, it cannot exceed the speed of light. When it exceeds the speed of light, it's no longer a particle. It becomes like a condensate, goes back to the superluminal level, okay, phase, without geometry or anything. So it loses its configuration. So when it condenses to the the subluminal level, which forms the particle from hot PDP mechanism, for example, then it has certain geometry of space. That geometry of space is what you are talking about. That it forms like two-dimensional, three-dimensional Euclidean, but it folds back and it finally forms the toroidal. That creates the continuity, connects with the superluminal thing. So that's space. But the time, what happens to the time is that the time is created with, for example, within that donut hole, whatever the hole is, the quantum level, the time is created. The Planck, I don't know, the smallest amount of time, that's a controversial thing, could be Planck time. And I believe there's a discontinuum length. Okay. That will get into the idea of gravity and things like that. But right now, I just concentrate on the time itself. So what happens is that the time is formed at the quantum level, the particles from partons to particle level. When it comes to the particle level, the time starts clicking. So the partons could be much less than the Planck length. Okay, so they are not. It's like a nucleus. They are not stable particles. But when the stable particles form, they are greater than the Planck dimensions. At that time, the Planck time kicks in and it locks in that particle at the speed of light, less than speed of light. And so the particle becomes stable. And when the particle becomes stable, that time, then it creates the time. It creates the event. And the mark of that event is time. Okay, so the quantum level, it creates time. And that time, we are not sure whether it's linear or non-linear. What happens is the particles start coagulating, therefore accretion of the particle occurs and it forms matter. And eventually it forms the mesoscopic level. So there are a lot of details like formation of protons and hydrogen atom, and then you have the fusion reaction, things like that. Eventually form helium and things like that. So a lot of chemistry to it. But then forms the finally mesoscopic matter, like we are on Earth. And the mesoscopic level, the times, much like the vacuum holds the speed of light constant, the mesoscopic level, it holds the time constant, the linear level. So it becomes linear at this mesoscopic level. But that linearity only applies like the correspondence principle, and I have proved it from the correspondence principle, that to the sound and light aspect, that's will be linear up to about, from the body that creates the time, about half a kilometer at the most. So beyond that, the time becomes non-linear. So what is that non-linear time? That's where it starts connecting with the world line, the astrophysical space. So it becomes actually more than half a kilometer. You can think it's astrophysical time. So you have quantum. So these times, then they come together. They form like a topology. You can think of like a virtual topology, like Caribou your space, Caribou your manifold. That makes the time constant, and the time starts like clocking or ticking away in that one, But inside of that, the time is linear, like in Earth, for example. But even on Earth, there are cells. So if we really talk about Earth, only like half a kilometer long, it will be really linear. Okay? If we go out of that, it becomes non-linear. That's why we don't get information. We can understand from information. Information and time are very closely linked together. So the information flows, the information flows from the, which way the information, time goes from the body to the astrophysical level. Information goes from the astrophysical level to the body. So that is what creates that flow going. And this manifold keeps the time constant so that it becomes like a clock. So each of that entity will have a clock. So like a half a kilometer, you can think of like a clock, and another cell will have a clock. And these cells now, this clock and the other clock starts communicating, and that's how the information goes. So that's why Einstein is partly correct. So I will stop about the time right now. There is more discussion, but I'll briefly want to mention, and then you can start discussing about that. Briefly mention about the gravity. The gravity aspect is that I believe that Bernoulli effect. You think of Bernoulli effect. So it's specific shape of the body, the matter, right? So like a wing. So it move the top of the wing, it starts moving faster, and from the Bernoulli principle of the pressure times velocity, it starts moving. So the pressure will be lower at the top level, will be higher, so it pushes it up. Now, I was thinking about a way it can happen. I can show by my hand, right? So it has a handedness or chirality to it. Okay. So your left-handed entity, I call it right-handed entity. But the left-handed entity will have this fluctuation or oscillation because of the Bernoulli effect. I had to go into details. I kind of sketched it out, but I don't want to show it right now. At some point, right now I just want to keep it audio level. But later on, I want to show that. So you have oscillation here. This oscillation keeps the terminal velocity here. So it goes like that. But this distance is, I call discontinuum length between the two. So that I work with Emery Taylor. I think that applies there. So they come only this much close, but they start fluctuating. What happened? This fluctuation, it creates like the Nobel Prize thing. They're saying for attosecond, it creates like a signal, because when they fluctuate, they are oscillation, they are resonance. They create a resonance, and this resonance peak, you get this peak, and I can draw a gradient. It's a levitating field. It's a levitating field. So if I do it right, my hands should go automatically. It's like a wing. I can make it, and it pushes the whole thing up. It's a gradient up. Now, complex conjugate of that. So if I say epsilon tensor of nu of gr, okay? So that is that gradient. The complex conjugate of that, if you find the complex, that has like a trough, like a gravity trough. So that is the gravity well. So that creates a gravity well, and that pushes the matter down. This is like a quantum gravity I'm talking about. So you see that? So you have a levitating field, and the complex conjugate is the gravitational field. Okay, so you can see the gradient. The two gradients are complex conjugate to each other. So at any point you can have this, and you can see that's true, because if the right shape is there, it will always float. It will always try to go up. But if the shape, normally the shape, what happens is that shape get rounded because energy, things like that. So it becomes like a ball. At that time, it's no longer levitating field. So it cannot levitate. So, and you can calculate that that it starts falling down. So how do our sense of up and down happens? This particular vector tells us the sense up or sense down. So it's associated with chirality. That's why left-handed entity, like left-handed particles and right-handed particles, become important. I think, I don't know whether graviton has a left-handed, right-handed, but that's my brief thing. So you can comment on that. I will go mute.
Okay, thanks. That's very interesting. I think you covered a lot there in quite a short space of time. Although, yeah, okay, so I do have a few points to make. I think you're absolutely right in terms of separating out the time and the space dimensions, because I'm sure you picked up on the fact that when I was discussing the unique hyperspheric model there, I didn't mention time, because time is not a dimension in the model as such. Could be added in later on and all. It's not an issue. So then if we're removing this six-dimensional subspace, yeah, I suppose you could then start questioning. Well, we're not removing it actually. We're just saying that the subspace that Christian is describing is actually four-dimensional at most, just like everything else in the unique hyperspheric model. So that kind of, what it does eliminate is the six-dimensional Calabi-Yau structure that he's talking about. So assuming I'm right, and I think I am, then what we're eliminating is the six-dimensional Calabi-Yau subspace. So if you're saying that that time is connected to that and we're eliminating it, then we're eliminating everything you talked about. Do you get me? I know you're on mute and all, but
yeah, let me. I'll come back on. That's okay. When you prompt, I can always come back.
This is it.
Then I'll let you do. Okay.
Well, no, I just want to, like, do you understand what I'm saying there?
I don't know what you mean by eliminating. Can you clarify?
What I mean is that, right. So you see, you can't answer if you don't know what I'm saying. So I'm saying that Christian is positing this six-dimensional Calabi-Yau space to efface all the sides of the cubes and make it basically just make it a grid that you can flow through. Okay, that's no problem. It's basically what he's talking about is a Lobachevskian space, but he never uses that term, right? But that is what he's ultimately talking about. So I'm saying that you don't need six dimensions to do that. You only need four at most. So that eliminates the six-dimensional Calabi-Yau space. Now, I'm saying that you're correct in the fact that, well, this leaves the model is open to interpretation about time. So you are free to talk about time within the model and create new models about time. That's completely fine with me. And if you want to add time vectors, yeah, that seems fine as well. But all I'm saying is that, like, you could come along and say, okay, well, I'm going to reposit time as a six-dimensional Calabi-Yau space. And that's fine. But it doesn't follow from the argument that we're just having, which is Christian saying that it exists and that it's a pixel issue. I'm saying that, okay, well, if we're discussing that pixel issue, we only need four dimensions. So already the six-dimensional Calabi-Yau space is out. So why it should be placed back in a time geometry isn't clear and would need like quite a big justification for it. But if you don't want to, you wouldn't have to supply that justification necessarily if you're just talking about extra dimensions of time and how they relate to each other. From that perspective, I don't have a problem. However, I do have a couple of issues with what you did say. So for instance, when you talk about when a particle becomes stable, time starts. You said that, yes?
Yeah.
Okay. Now, do you see any problem with that sentence?
I don't know the reason, maybe clarification, but I don't know what your
okay, well, I'll give you a hint.
Of that.
It's at the start of the sentence. The word when. What does when indicate?
That's a good point. Okay, at the when, I may not be totally wrong about that, but the thing is, when implies time, right?
Yes.
So it is a catch-22 in that sense that that's the time comes first and the stage, or that's the becomes stable.
Well, wait a second. Your sentence is very clear. When the particle becomes stable, then time starts. The time already has to be in place because it's talking about when.
That's a good point. That's an excellent sentence to analyze.
Yes.
So I don't think I'm completely wrong, but what I imply, I can.
I'm not saying you're wrong. I'm just asking. You need to resolve this. You need to resolve that contradiction.
I want to.
So how are you going to do that?
Yeah. The thing is that
have you got this sorted out? Have you got an answer sorted, or do you need to think about it? Is the question.
No, I think it's a catch-22 in the sense that that's a very close thing in the sense that not when. If the particle becomes stable, then the time starts, for example, right? That's one statement that can clarify that. If the particle becomes stable, that's just a condition of stability. It is nothing to do with time. So if the particle becomes stable, then the time starts.
So you're saying it's conditional. It's a conditional thing.
Yeah. But is it that way? Or at the same time, simultaneously, does this event happen simultaneously? That you cannot really distinguish, like a superposition type of thing.
Well, when you say if this event, Rajan, what is this event? Do you mean
the stability, the stable particle formation?
Okay, but you're talking about simultaneity, so you're talking about two events. So what's the second event? Time start.
The second is the time itself. So
right. But isn't that weird? Because simultaneity has to do with time. So
So the thing is that it's like
so you're saying the particle becomes stable, then time happens. Well, then that's a time thing, right? Because there would have had to be some amount of time would have had to elapse between the particle becoming stable and time starting.
That may be a better way.
Then you have two types of time, right? You have the time, whatever that is, and then the time that's counted between the particle becoming. Also, I have a problem. I mean, you're talking about particles here, but the universe is filled with particles. So let's say, and well, we'd also have to discuss by what you mean by becoming stable. But let's say there was a particle over here, it becomes stable, and then there's another particle over here that hasn't decided whether it's stable or not. So the time is started over here, but not over here. Is that what you mean?
Yes. Yes. So the clock starts here.
That seems a very confusing idea.
No.
I don't really want to go down that route with you just yet, but maybe if you need like a much more. I think I need like a bit more of a solid framework, like maybe I don't even know, like the cubes that Christian is talking about.
Yeah.
Anyway, that I need to read something on that. That's a little bit strange. But I would like to just talk about multiple time axes. That sounds pretty interesting. Yeah. Well, I have an issue with it. Let's say we are going to put them into like a Calabi-Yau structure, because why not? That's what you're suggesting. So then we're saying that there's a time axis here, and then there's one orthogonal to it here, and a third one, and then 4, 5, and 6. Okay, so now in 3D space, we have 3 orthogonal dimensions, and time is going on throughout those. But it's only one dimension of time, right? But that's what we'd all agree, that we have at least time is flowing from the past to the future. So it's linear. Well, it feels linear, and it's one directional, right? So that's what we consider. But then is it really one direction? I mean, if we're talking about relativity, then we've got time slowing down and speeding up, and it's linked with space, but it is supposedly okay. So we have that. But then if we're going to introduce a linear time, and then we have another orthogonal time. Now let's say on this axis we go 1, 2, 3. We're counting up, and on this axis we go 1, 2, 3, 4. You know, and we're counting up in both ones. But then we say, well, then we have time coordinates, don't we? We have like at moment 1 here and moment 1 here. There's another space called 1, 1. But then, you know, we can go like 1, 2. So if one axis is, one of the time axes is x and the other one is y, then we can speak of, I don't know, different events that are like, you know, happening at time x and time y and such things. I mean, that's interesting, but what does it mean physically? What does it mean from our experience? I don't think it means anything from our experience necessarily, but you know, so that would be my contention there. Do you want to address that?
So I think time is closely linked with rotation. Like I mentioned last time.
Okay, yeah, but just like, what do you think about what I said there? Do you think there's? Yeah.
See, just, you know, like time you said about time x, time y, and time z, right?
Is this like? Is this anywhere close to what you're talking about, or is it? I mean, would that not be a logical way of discussing what we're talking about?
Yeah, there's a slight deviation I have to do. The reason is that, you know, there's a rotation. Okay, you can think of.
Okay.
I can. Let me. I have my phone ringing, so let me.
No problem. No problem.
Okay, so now it's okay. Now it's clear. So one of the things we have to distinguish between rotation and rotational space and you know, linear space or spatial space. The reason is that rotation is around a point, what we call as a point. But suppose we are just rotation. I mentioned last time, orthogonally, if you divide the solid angle 720 degrees by 90 degrees, you get 8 dimensions of rotation. Now, the other 2 dimensions of time are radial, okay? The radial thing and the tangential. So those are the space unit. The space units are there. So we got to talk about rotational unit called omega or whatever, or theta or omega. And then you have the radial r and the tangential length TL and RL. RL is the radial length and TL is the tangential length. So if we have that, so if you have omega, like I said, if you divide by 90 degrees orthogonally, you get 8 of them. So you have 8-dimensional rotational space. I won't call it rotational space. 8-dimensional rotation, and then 2-dimensional space. So we can think of that. So dimensions, I think totally 10 dimensions make sense to me, because if you look at our fingers, we are left-handed, right-handed, and that's making it dynamic. So which means that we should have 10 dimensions because of the left-handed, right-handed. If we look into that, I talked about 5-dimensional space, but that is only one aspect of it. If you want a dynamic thing, you have to have 10 dimensions. That I agree. So I think the total dimension should be 10. Now, how does it add up to 10? That's the whole question. So if we talk about, see, you have polar coordinates, you have spherical coordinates, things like that, right? We can do the transformation. So it's a transformation aspect. You know, you are transformed from the rotational space into Euclidean space, vice versa. So we get different results. So what you're talking about is a Euclidean geometry, time x time y times z. That is the Euclidean geometry. But if you are talking about polar geometry type thing or spherical geometry, then you define it by thetas, and all of the physics, even Einstein physics, does talk about spherical coordinates versus Euclidean coordinates. So we have 8 dimensions of time of rotation and 2 dimensions of space. So that's one aspect. But what happens to space? Evolution. So evolution happens. I believe evolution happens because when a particle is formed, like by Hot PDP mechanism, we know that clock starts. The clocking starts, the clocking network. So each particle is associated with a clock. That's why they have a specific energy, things like that. Okay. So each clock is associated with a specific quanta of energy. Okay. So that particle form, that clock starts clicking in that particle. So then that particle will behave like, for example, it forms like tritium matter or something like that. Then it starts decaying. Could be associated with vacuum decay, I'm not sure yet. But it starts decaying when it becomes isotropic. So the clock starts, so it starts radiating things. So each particle will have a clock. That becomes real. Another side, the hot PDP mechanism is going on, but it has not stabilized to the level that forms a clock. So you are correct. In one particle, the clock starts and the clock is there. That's real. The other place is part of superluminal thing. It's still part of superluminal thing. So it's not real. So it becomes partons. It is going, going random oscillations, fluctuations, or 0-point fluctuations, and it has not enough energy to lock in a particle yet. So the idea that the process goes on randomly, but it creates like a mechanism which stabilizes that particle because it creates a specific energy level. So each particle has a specific energy level, like a frequency, and then h nu is that particle's specific energy. Like you have electron, you have positron, or something else. They have specific charge and specific energy. Then forms other particles, eventually proton, things like that. Again, that particle has a specific energy. That energy is that clock. It creates that clock, and that proton becomes stable for that period of time. It has a residence time. It's not stable forever, but it's stable enough that it can combine another electron and it forms hydrogen atom, and then it forms isotopes. That's a complex mechanism. We still have to figure out. I think we can figure out from this one by very careful arguments, step-by-step argument. There are also calculations. We have to do math calculations to justify each step, and then you can build up how they build up eventually helium atoms. So the chemistry, the whole periodic table of chemistry, eventually to form a stable matter, and then it forms. And then the chirality automatically tells that the life can form automatically. The carbon has a specific property that it creates a mirror symmetry and all those things that can create life, where the oscillations are kept at certain. So hemostasis, things like that, where it keeps a temperature and things like that at certain level, and the cells form and the cells starts stabilizing. So you have from amoeba all the way to human beings, all the cells are forming, and it's closely connected with signal to noise ratio. I was mentioning in another paper. I was mentioning it. So I think they are all, for me, they all add up, but we have to be very careful. Like you mentioned, we just now are concentrating on how the dimension starts, and I believe from what I argue, I think there are more debatable things, but I believe your 4D geometry of space makes perfect sense to me, the toroid or something, and that's it. for space, geometry of space. For topology of time, I don't want to call it Caribou. That may be a confusing thing, but I would just say six-fold dimension, six-fold time dimension, and a four-dimensional space dimension. I would simply say that. Now, I just say Caribou here just to say a stabilizing structure, manifold, but it's actually a virtual structure. See, time actually it's a virtual structure we are imagining, but only space is a real structure. So from that point of view, I do agree that the question of whether Caribou-Yau manifold should be reserved only for space and not time. So that's my point. So I will again mute my. You can start.
Yeah, interesting points there. Hang on, I might open this curtain a bit. It's a bit dark in here. So that's better. All right, so pulling over here. Yeah, good points, Rajan. I see what you're saying. You clarified quite a lot there. So I think one of the important points you made was that each particle is like a clock, and yeah. So Rajan, you don't need to mute yourself. I don't mind discussing what because these are your ideas. So I don't mind discussing those. So yeah, we have particles. So there's a couple of things there that you said about rotation. Now, if we talk about rotation, it's a rotation in an axis. So it's and those axes are dimensions. So when we talk about, so really, you can't really move from to get out of it by saying, well, I'm talking about rotation, because rotational dimensions and dimensions would be equivalent. But I don't think that's a huge issue that you're raising. Although I did mention this in the previous one about you mentioned this solid angle thing, and 90 degrees goes in there 4 times or 8 times, so therefore 8-dimensional. But I was thinking about how to more better describe what I was saying. So here it is. If we have a circle that has 4 90-degree angles in it, but notice that, so let's say we call them X and Y. This is the Y-axis, and this is the X-axis. That Y-axis has plus and it has minus, and the X-axis has plus and minus. Yes. So there's only 2 axes there, hence 2 dimensions, even though there's 4 right angles. Do you see what I'm saying? So therefore we say the circle is 2-dimensional and not 4-dimensional. And hence when you have a solid angle, which is 720 degrees of rotation, it would still only be 2-dimensional, because you're just going back over the same 2 dimensions twice. But so that's just to clarify that point, because I think a lot of physicists seem to have a real confusion over what is meant by dimensions, and because in data science we have you can have a data set with millions of dimensions or hundreds of thousands of dimensions, but those dimensions they can be things like color, and so when physicists and mathematicians talk about dimensions, sometimes they're actually talking about, they're getting mixed up between different terms used in different so that's something to consider. We could have a 3-dimensional graph, of course, and then because we can't graph a 4-dimensional space, but we can add the dimension in, the values of the 4th dimension in, using color. So then in that sense we could say, oh, the 4th dimension is color. It's not really color, it's just how we're visualizing whatever that 4th, and by dimension meaning just a value, really. So because I mean that dimension, that value could signify something other than a spatial dimension. It could be heat, so it could be spin or or electric charge, electric density, charge density, and so forth. So those are all interesting points and points to keep in mind, you know, going forward. So what else did you say, Rajan? You had some other good points.
So the other aspect to clarify, I think a visual, like, you can think of an umbrella, right?
Yeah.
So when you have an umbrella, you have a point. You have a point like this one, and you have many what you call the sticks or the ribs of the umbrella joined at this you know, what you call as the ball in the middle. So you have these ribs coming up, and the ribs then form umbrella shape, right? So you can rotate that umbrella this way, right? And the ribs can be put as 90 degrees. That's one side of the umbrella. Okay, that's only half the proportion. Okay, we have another umbrella on top, or you put another umbrella like that at one hole. So now you have more things. So suppose I put one umbrella here, one umbrella close on top. I have at least four at the bottom. I can put, and the 4 at the top. So totally I have 4 plus 4, 8 of the rotational, because at the rib they join together in the middle, and that's the rotation. So I can rotate it this way, right? The umbrella, but the dimensional space are only the radial dimension. The rib, eventually forms like a radial thing for the umbrella, and there's a tangential thing for the umbrella, the length of the umbrella, and the radial and the tangential form the curvature of this umbrella. So you can think of an umbrella. I think that's a good analog to visualize how the rotational space may be working, or rotational elements may be working with spatial dimension. So umbrella analogy may be a good way to exemplify that, or man.
Yeah, I think it is a you know, it's an interesting concept, but again, it's sort of going away from what you were originally talking about and moves into a slightly different area, and that's okay. But again, yeah, it's not the worst thing.
You got to transform.
Anyway, it's just a small point that I was making, really, but just to consider that. But yeah, so I think the other points you were making were to do with the time issue. What was it you were saying, the other beyond, because you actually touched on quite a few things there.
The clock starts with the particle.
Well, there was another issue to do with discontinuum physics. So I know your area where you'd have like a point here, and then kilometer away is another point, and then those two things are discontinuous.
Yeah.
That's what. Let's say we're not talking like kilometers, just to make things easier.
Quantum level. Yeah.
Or even just. Well, let's say we're talking about the distance is a meter, right? But then if I were to select 99 centimeters, so I just move 1 centimeter to the left of this point that's discontinuous from the other point, then that point is it discontinuous from like minus a centimeter, or like if you were to plus, you move 1 centimeter to the right, so you're now at 101 centimeters.
Yeah,
presumably that point discontinuous from you know, 0 point, or like, you know, in coordinates 0 on the y-axis, comma 1 centimeter on the z-axis, because we're just using a thing as a one-dimensional plane. So then obviously if you take very infinitesimal little movements, like let's say I have a tennis ball and it's sitting there, you could take infinitesimal movements inside the tennis ball and say, well, this point here is therefore discontinuous to another tennis ball, and You know, I guess I don't really understand what, like, this is all timey-wimey space-time stuff. So I think I have a bit of a difficulty conceptualizing that. I suppose in space-time and in relativity, the ball is like a cohesive object. So, and if you were to accelerate it, there's a discontinuum there, isn't there? Because, you know, at what point does the field, the world line of the ball, end compared to a stationary world line of a ball that's not moving, for example? So that's the discontinuum, right? There's time is moving slower for the ball here, but not for the other ball. So how far does the discontinuum extend, I guess? And also in time, how far does it extend? Because acceleration takes time to occur. But I think they've been looking into that, and they think that it's like very small, isn't it? I think you have I thought your equation said something like 500 meters. Maybe it's...
Yeah, actually, what I mean by discontinuum, okay. To understand more about discontinuum, I think Emmanouil Taylor's arguments, we have like 8 papers now, but some of it is his own paper. Like I didn't, you know, I went there to quantify that. So I quantified that discontinuum physics for Emmanouil Taylor. That's why I came into picture. I think I'm quite confident, happy, you know, very, I think we have a breakthrough there. But out of like 10, 12 papers, I think myself and Emmanouil Taylor may have 6 to 8 papers now. I think it's, and the last paper, the you know, physics essays, is a fairly good reviewed paper, fairly high level, and you know, he has done a good job, Emmanouil Taylor, along with me, and the reviewer says it's an excellent paper, you know, and we have the comment there. Only he wanted very minor revision. It's about Bohr's atomic model and probability theory. So he's essentially falsifying all these things, you know, Einstein thing, each one. But his argument, you should go through his argument about Einstein experiment, and he nicely describes the Bohr you are talking about, things like that. But what I am talking about, the discontinuum length, is at the subquantum level, like 10 to the power minus 26 meters. So that's the minimum distance. You know, what I'm saying, you cannot go any smaller than that, you know, in the real sense. So if we go smaller than that, it becomes superluminous. So hot peak mechanism will stipulate that the minimum distance, the minimum length, has to be something like 10 to the power minus 26 meters or something.
Well, wait a second. Isn't the Planck scales whatever
times the speed of light? So 10 to the power minus 34.
Wait, hang on. The Planck scale is like 6.6, something like that, 10 to the minus 34.
But second, right. I'm saying time. It's the time. It's not the space.
Oh, right. It's the time. Sorry. Right. Go ahead.
So I believe that it's the time. It should be time, not the space. So for finding the space, you have to multiply it by the speed of light. And then you get to the 10 to the power minus 26 meters. And that is the discontinuum length. That's the smallest length.
Wait a second. You're talking about, okay, you're talking about time. So why is it in meters?
No. 10 to the power minus 34 seconds, right? Approximately.
No. The Planck length is 10 to the minus 34.
No, I'm talking about Planck time. I believe in Planck time, not Planck length.
Oh, but what was, okay, but what was 10 to the minus 26? Is that not time?
Okay. No, 10 to the minus 34 seconds, right? To convert into length, you have to multiply by the speed of light.
And that gives you 10 to the minus 26.
Yeah, that's the length. That 10 to the minus 26. That because speed is meter per second, and you multiply by the second, you get meters, right?
Yeah.
So
I mean, I don't know about that exactly. Speed is length divided by time. So right, you multiply the you multiply by the time, and you just wind up with, right? Yeah, fair. Yeah, I get that. Sorry, bit slow.
Oh, yeah. No, it's okay.
Okay.
So,
yeah.
So that's how you get. That's the minimum. You cannot go anything below that. If you go below that, it becomes unstable particle, and then it becomes part of the superluminous thing. It becomes part of the superluminous condensate, so to say. So it becomes like a proton or something like that. It's not a real particle. So 10 to the minus 26, according to me, I don't know whether that's a fixed thing, but based on the Planck time and things like that, I believe that's the discriminant length right now. The smallest discriminant length is 10 to the minus 26 meters. Okay, so that is the one that keeps between left-handed and right-handed. So if the right-handed has to have a separation distance, right? Because otherwise they don't exist. Right-handed and a right-handed. So if you have left-handed particle and a right-handed particle, okay, I call entity because I don't know whether you can call really particle, but entity is typically a particle. Okay, so you can think of a left-handed particle, right-handed particle. Not all particles fall in that category. You see that? So it's a special type of entity. The smallest level of entity, it could be electron, it could be positron, whatever. So if you have left-handed and a right-handed entity, and there's arguably, what is left-handed? I think you have done a lot of work on that, left-handed, right-handed. And some of the, you can have left-handed, not right-handed, things like that, right? So, but the minimum distance, you have to keep a minimum distance. That minimum distance is the discriminant length, which is 10 to the minus 26 meters. So these two ends of the right-handed, they keep 10 to a distance of 10 to the minus 20. And that separation distance keeps the chirality intact, or in the sense that there will be a left-handed particle, there will be a right-handed particle, and they can come together and they can oscillate and they can create this gradient, So I think we should be able to calculate these things. I think I feel like
Well, that was it. The other point. I mean, I don't know if we covered everything that you said, but so I suppose the other issue you were talking about was gravity. So we might as well move into that. But the levitation field. I'm not. So what you're talking about, the gradient between a right-handed and a left-handed particle is a levitation field, or is that a different point?
Yeah, actually, what happens is that there's a minute fluctuation. Okay, minute fluctuation because of the Bernoulli effect. There's a quantum level fluctuation. I don't know if it's 0 point or Sitterbourg or something like that. That we have to find out what is associated. But it's an oscillation of because of the Bernoulli, the pressure, the Bernoulli effect. The oscillation because of the velocity and the pressure are trying to balance each other. So there will be oscillation of this left-handed particle, and the oscillation of the right-handed particle. And when they come together, these oscillations, they can create resonance because they match the oscillation. Okay, they give a constructive interference and a destructive interference, right? And they talk nicely. You look at the Nobel Prize ceremony. That guy, that physics guy, expert, who is the one who is choosing the Nobel laureates, he's an expert in that. He describes nicely about attosecond, how the attosecond. So he talks about that, but he didn't talk particularly about resonance. But what I'm talking about is a resonance, because the frequencies match, they produce a constructive interference. And this constructive interference is the resonance. Like a laser like thing, the constructive thing that creates that gradient. So you have these, they are fluctuating here, these two, and they create this gradient, up gradient, up signal, which is like a gradient, and you can think an axis that falls that between them. Axis that falls between them. So that is the up signal. That's I call the levitating field. Okay, and then complex conjugate of that will be the gravitation field, which is like a well, gravitational well that forms. That's because of the symmetry to start with. It's a symmetry. If there is up there, there has to be one down here. Noether's symmetry theorem. So that's how. So it forms like that. Like you mentioned, I think in your anomaly detection, there's up here. There's something down here to balance that. So it's like a static wave or something that forms. So you have one up, one down, and they balance that energy. So the down is your gravitational field, and the up is a levitation field. So there is always a balance between it. So whichever wins that game is the one that is pulling it. So the gravity, in the case of gravity, which is determined by the shape, by the way, the shape determines the mesoscopic level, the shape. You can see, you can have a paper and you can drop it from height, slowly it descends. It has a terminal velocity, right? It doesn't fall immediately. If it's a big paper, if you have a big paper and you drop it, it doesn't fall like if you have a ball, it falls immediately. Okay, so that is quantum gravity. I mean, Galileo, of course, didn't use that, but he said eventually everything falls down. That's all he was saying, like a leaf or a feather or whatever, feather and a ball. If you drop, they fall down, right? Eventually they fall down. That's because the gravity wins, and you can figure out why that gravity wins in the end. The Bernoulli effect, because the shape. What happens to the shape? This shape, the wing shape, is hard to keep because at energy level they start to round up. When it becomes like a ball, it's no longer Bernoulli. The Bernoulli is not just on the top, but also at the bottom. So, and then when you calculate that, you'll see that the gravity wins. So the down thing wins because of the stratification of Earth itself. So you have to look at the Earth itself, and Earth, like you mentioned, like your positron, things like that, in the center of the quantum density, you have to talk about quantum. I'm talking about that. Actually, CJ Pass, he's going to publish 2 of my papers now. I think they talk about that, and not a strong gravity, weak gravity. So there are 4 papers I have. I talked about briefly the concepts behind this. So the stratification of the Earth, right? The center of the Earth, why it pulls towards the centro attraction. Like always, every object is pulled to the center of the Earth, right? That's why it's called the center. So it's like a virtual. I believe that it's a virtual center. It's not actual center. It's a virtual center. But because of the shape, because of the geometry, it forms like that, concentric circles. And you have pressure. If you look at the pressure, it will be higher inside, and it becomes rarefied as you go out. And that creates a space, and up to the space, it becomes almost like a vacuum, zero pressure. And that's zero gravity there. So you have a delineation or a disconnect between that thing, and becomes zero gravity. So no longer, if you go, the satellites are not pulled to the Earth because they go in a concentric circle enough to create the centrifugal force to balance out the centripetal force. So you have a radial dimension, a radial gradient. Then you have a tangential divergence. So what we are talking about, gradient and divergence. See, last time I couldn't get that picture. Del dot F is actually divergence. That's what we are looking for. The divergence. Like in your equation also, del dot F, whatever that is, del dot something. That's called the divergence, and del cross is the gradient, the curve, whatever it's called. So you have these 2 aspects finally about the field. The gradient field I talked about, and you have also a divergent field. So this has a divergent field. So we have to talk about divergent field here, a gradient field here, and then we can do the math very similar to Maxwell thing. And I think we can figure out how. Then we have to prove why there is an asymmetry, asymmetry. the asymmetry, how does the asymmetry, so they will only balance each other, right? But how does the asymmetry come so that the gravity wins over the levitation? How does it connected with the shape? The shape creates the divergence. So
okay, but aren't you like complicating things then if you have a, you know, like we have asymmetries in physics in general that are kind of irritating, such as like the leptogenesis, you know, matter-anti-matter asymmetry. So if you want to introduce another asymmetry in order to explain something, that's...
No, they may be connected. They may be connected. The baryon asymmetry, right? You are talking about baryon asymmetry? Is that the one?
Well, yeah, well, you know, the matter-antimatter asymmetry.
Yeah, isn't it called baryon asymmetry normally? I mean, in general?
Possibly, but it's also an issue. It's called leptogenesis because when the leptons were created, the genesis of them, there was more matter created than antimatter. And the question is why? Because they should be completely symmetric. And of course,
it's connected with gravity. Yeah, it's connected with gravity.
Anti-gravity would need to be completely symmetric as well.
Yeah.
So your question about, so it seems like you're introducing, so we would call leptogenesis a problem that needs to be solved in physics. So it sounds like you're introducing the same problem in gravity in order to attempt to explain gravity. And that's probably not a good way to go because...
No. If I can explain that, automatically I can explain the leptogenesis. If I can explain why there is an asymmetry between gravity and levitation, I can automatically then justify about the leptogenesis.
Well, no, but hang on, because
gravity creates matter. Gravity creates matter.
Well, but antimatter is still a gravitational phenomenon. It's not anti-gravitational.
Well, actually, gravity, what happens is they create more matter. Gravity tends to create more matter than antimatter. You can actually argue that.
I mean, yeah, you can argue anything.
No, you can actually prove it. I'm sure you can prove it.
Okay. Well, I've been looking into quantum gravity as well. So I have some stuff done on that. But would you believe that I'm trying to run it here and it's not working? So, but
what is that? What is that about?
Oh yeah, I can show you. I might as well just. I probably show the paper again, eh? And we'll see if I can find that. So you know, with the monopoles that I've been working on, four-dimensional gravito-tortio magnetic monopoles, I think they are. So in that research, essentially what it boils down to is that you need to hang on a second.
Are they direct monopoles? They are not direct monopoles, right?
Oh, they could be, yeah, because they're completely straight lines. I mean, they're linear, you know, but
so they're like a string. They have like a direct string and things like that.
They're more like a ray of light, so they're completely straight. They don't bend, as far as I know. So what you can do is, with the equation that I was developing based on Maxwell's equations, which has a gradient for the, I'd have to look it up again, but it's like, basically we're looking for the gradient, a magnetic ray or current that produces an electric gradient, as opposed to an electric current that produces a magnetic curl. So this is the kind of concept we're looking at, or it could even be a magnetic gradient, you know, from a magnetic current.
Actually, thinking of it, if you can prove the asymmetry there, that magnetic vector is a primordial thing and not the electric thing, I think that automatically, in a way, can argue about all these asymmetry aspects, gravity asymmetry as well as baryon asymmetry. I think.
Well, yeah, it's interesting, but I suppose I'm trying to look for a very symmetric equation, but you know, it is kind of, what's the word? It's very theoretical, so there's room to move around and suggest, well, maybe there isn't, maybe there is, as you suggest, an asymmetry involved. That's completely reasonable. So, did I just get out of that? Can you see that? Oh, you can.
Let me. I'd use zoom a little bit.
Yeah,
I think I can a little bit. Just to fill the paper. I mean, just to fill the screen there.
Okay.
Maybe like a little bit. Yeah. Maybe. Yeah, that's fine.
Okay. I'll zoom. Not zoom, but I'll move down here and So those are the equations. So remind me here. We have we have Ampere's law, and then this one is. So this would be the
divergence. That's a divergence. Yeah, that's
right.
Called a divergence.
So on this side, then we have the magnetic monopole current, and we see that it is electric charge density over, what is this, permittivity?
Yeah.
Epsilon 0.
Yeah.
Divided by, or no, sorry, plus the magnetic monopole current, which is a scalar.
The flux, magnetic flux.
Right, but this is
differential, time differential of the magnetic flux.
Exactly. So this is measured in Teslas. So ultimately, this becomes Teslas per second squared. Yeah. Mm-hmm. So if we put this into Mathematica, right? It's this value divided by this value minus. It could be plus or minus depending on how you do it. Mm-hmm. 1 Tesla divided by second squared. So there's the equation. And this is what they give you as a result.
The plot.
This is the kind of the shape. So, and that's okay, but that's obviously automatically generated, so it's not technically spot on what we're looking for. Now, I haven't run any of this in a while, so this might be the wrong notebook. In fact, I think it is the wrong notebook. These are old equations I was attempting, and they didn't really work. So hopefully the newer equations are in here somewhere. I may have to set this back for another time when it does work. Okay. But if I can figure out how to get this to work, okay, it doesn't look like it. So I'm not really too sure. I'm just going to run all of these, and we're going to get a lot of errors. But maybe it'll work though if I run all of them. No. Oh, that's not right. Okay, it's still not working. Essentially, this is the 1D case. Mm-hmm. So if you imagine we're out here, this is kind of bigger. So as we get to like a smaller and smaller degree, we see that gravity in this quantum mechanical sense, it doesn't go to infinity. It goes to a very small amount. And then as the magnetic monopole begins to spin in the other direction, it again, as the density, see there's different dimensions here that it should be appearing there. Hang on, I might be able to find the graph.
It's like a mass density and charge density. It's different things.
Yeah, a little bit. Sorry about being so disorganized here. I was not really. So it's a bit of a shame that this isn't working the way it ought to be working. Right, so I do have the graphic somewhere, but basically, yeah, there's different dimensions. So one of them would be the Tesla, so the spin of the particle, or sorry, the spin of the magnetic monopole. Right. Another one is the charge density. Oh, but then the charge density, you see, is like, you know, has two components. It has the energy divided by the volume. So when we look at those three dimensions, then energy, volume, and the spin of the magnetic monopole, those are the three dimensions effectively of our graph that we're going to make. And as the volume decreases, you know, basically as the length scale that we're measuring decreases, we can see that we get this kind of curve at the end here where it doesn't go to infinity like it does in other models. It just flattens out. Yeah. Right. And then as the volume goes negative, see, you need a 3D version here, but as the volume goes negative, then I believe the gravity goes in the opposite direction. It goes positive.
So what do you mean by volume got negative? A hole? It's like a hole? Volume going negative? Is it like a hole?
Oh, no. Yeah, it just goes down because it's saying that the strength of gravity is increasing because gravity is a negative force, right? Pulls you down. So as the electric charge, we could take another value and say, as the energy increases, which is equivalent to the mass, the gravity gets stronger. Yeah?
Attraction. Yeah, that's right.
Right, yes. But then if we talk about the spin of the magnetic monopole, so as it's going positive, as it increases in its strength positivity, the gravity increases in a negative way. But as it increases, as it starts spinning in the opposite direction, and as the volume goes into a negative area, then we have some other issue where its gravity inverts and becomes anti-gravity.
Is it like you are spinning inwards versus spinning outwards? Like the concentrically goes inside and one situation, and then it comes out. It kind of curls out outside. You know, so you have the concentric thing that goes inside. The field keeps converging. The other one, the field keeps diverging. Is that possible?
Well, when I'm talking about the spin of the magnetic monopole, so I'm just talking like about if you think of it as like a ray of light and it's spinning in one direction, then when it stops and starts spinning in the other direction, that's when
clockwise and anti-clockwise.
Yeah, exactly. So possibly an opposite spin could cause an anti-gravity effect, but then maybe not. Maybe it is I'd have to look at the graph to be completely sure, but like I said, I'm having trouble locating files here for some reason. But let's say it was the volume, right? So that this is another way. Like if we talk about going back to like our tennis ball or an apple is kind of a better example for gravity. The apple has a volume in space.
Yeah.
And, you know, so that's whatever that is, you know, but if the volume was negative somehow, if when you did that equation, you got a negative value for that volume, then that apple, if you could see it from its inverse location, where it's still it looks like an apple, that will have a positive gravity associated with it because it has a negative volume. So negative volume is obviously completely unphysical.
Like a black hole, very similar to a black hole.
Well, no, because I'm suggesting that, well, maybe from our point of view and our reality, it would just not exist. Just it wouldn't look like it's there. But
how do you visualize a negative volume? How do you visualize a negative volume?
Well, that's it. I'm not suggesting that we should visualize it. I'm just saying that if I have a dimension that's measuring volume, yeah, and that can go to zero, we can say there's something with zero volume. Then we could also say, right, and our dimensional scale is going into the negative as well. Which
mathematically, just mathematically.
Yeah, just mathematically. Then we're talking about a negative volume. So we can just analytically extend our equation into an area of negative volume to see what happens to the gravity. And we discover that in that case, we have anti-gravity, repulsion. But obviously, we don't see repulsion in the universe. We don't see anti-gravity in the universe. But likewise, we also don't see negative volume in the universe. So it stands to reason that these two things will be connected. Does that make sense?
So it could be like the dark matter, that kind of thing.
Yeah, maybe there's some connection. I mean, certainly, you mentioned black holes. But I mean, black holes are obviously areas of intense gravitation. So it doesn't seem correct. Like if I was to shrink the apple so that it became zero volume, then it would be a black hole. But then if I continue shrinking it so that its volume becomes negative, so it begins to expand again, but with negative volume.
Wormhole, not wormhole.
Right, but then we're saying that object that formerly had infinite gravitational strength now has a negative gravitational strength. And then that's contradictory because let's say it's like almost at the limit of zero, it's already got infinite, it is a black hole, right? So then when it hits zero, it's still a black hole. But then when it's at the limit on the other side, the negative limit, now suddenly it's repulsive. Now suddenly it has repulsive gravity. That doesn't make sense.
That's like a wormhole. Wormhole, I don't know.
No, consider what I'm saying, because if it's like what you're always talking about. So if we're coming at it the limit from the positive side, it's getting infinitely strong gravity. But if we come at it the other way, the limit as we go to zero will be infinitely repulsive gravity. But both of those meet at the center, and the center must be zero. So either we're talking about two different universes where in one universe, when the apple collapses, it becomes infinitely repulsive. And in the other universe, as it collapses, it becomes infinitely positive. But if it's both the same universe, and it is possible to have an apple that inverts and becomes, has a negative volume, but still looks like an apple, then the 0 point would have to cancel out. Because, like when I say zero, I mean, zero volume. Both the infinitely attractive and infinitely repulsive aspects of the gravity would have to cancel out in some way, meaning that when you have an apple of zero volume, there is no gravitational, it just doesn't exist. But I don't really like that answer. I'm merely, spitballing, as they say.
Yeah, but like a great, I don't know whether you are hinting at great attractor, great repeller type of thing.
No, not at all. Oh, well, yeah, sorry, I was thinking of just strange attractors. Great attractor, great repeller. It's plausible. I mean, there's something there, possibly future, but this is real. This is really typical that I can't find this picture and that none of the equations worked. That's real typical, isn't it? Let me just think.
Well, I think asymmetry of the fields are quite. I think I will think more about magnetic versus the electric asymmetry of the fields. I think they could be.
Well, yeah. I mean, I think it could be interesting if there's a logical contradiction. Or
I think
something.
It can explain everything else after that, based on that.
Well, yes, plausibly. That's something to look into.
And you can use Maxwell type equations after that, and your equations, type thing, and all that divergence and gradient divergence of the fields, and we can show that if the monopoles exist, for example, it automatically means there's asymmetry of the magnetic field. So the very aspect of the monopole will create the asymmetry enough to create the baryon asymmetry. So it may be all tied in. So the monopoles exist in the supernova.
Yeah, I think it's probably worth looking into.
Yeah,
it could be a bit of a long shot. I don't know. Okay, well, since the other thing didn't work, I'll show you some other research that is related to. Remember, we were looking at I was asking you to create a space-time metric of inverted stereographic projections, and I think that was tricky anyway because, well, like I say, there is no time element to these metrics, so there's really no point in creating a space-time metric. But during our discussions, you mentioned kernel, something to do with kernels.
Yeah.
Now, I'm not entirely sure how that works in terms of space-time
geometry. Kernels are the matrix,
it's like polynomials and all of the Gaussian stuff. So, I've forgotten exactly. Well, just like basically kernels is a good enough phrase for what we're talking about here. But there is that, we do get that a lot. It is a thing in relativity, isn't it? Where you have those rings. Yeah. You have like a contour plot. I'd have to look it up again, what it's called. But I think isn't there a conformal, it's something to do with where you have these rings and you can draw a line, like how many lines does your vector cross? And then if you draw it in a different direction, it crosses a different number of vectors. And you can expand that out into 3 dimensions, instead of having it flat. And anyway, so that's what you were talking about. You were talking about the nonlinear distribution of the galaxies, which I thought was really interesting. So I went ahead and I did that with the support vector machine. So you can see that, can you?
Yeah.
Right. So there's all those galaxies plotted in the universe, and in the center, it's the same number of galaxies but inverted through the stereographic projection. So they're in the center, and this red line here shows the hyperplane or the decision boundary between the two clusters, right? And so zooming in, then we see that the hyperplane is located behind the first great wall of galaxies. So Earth would be here at the center, and the first great wall of galaxies that we encounter is these. Then we have the hyperplane, and then we have the galaxies outside. And then if we to invert all of this into the center, we get this, and this yellow line around the outside here is the Great Wall, and all the other galaxies are inside. Obviously, if Earth was there, it would be obliterated in this scenario.
So Milky Way galaxies inside that?
This is what I'm not sure about. I assume it is. I assume that the Milky Way is located centrally in this graph. So yes, the Milky Way would also be inside this. So yeah, that stands to reason. So what this appears to suggest is that when everything rotates in, these galaxies out here along this ring will not rotate in to the center. They are actually within the boundary of our local sphere. So if you think of it as if it's a 4-dimensional hypersphere universe, let's think of it as a 4-dimensional cube, because that might be easier. The inner cube is here, roughly, so somewhere inside here. So this yellow blob exists within the inner cube. and then the 7 cubes that connect to the larger outer cube, which is here represented by the red line, are in the intermediate space, basically this area where there's very few galaxies. And so these galaxies are on the very, so let's switch back to talking about hyperspheres, because this is a round thing. So on the surface of the hypersphere essentially exist all of these galaxies. And because of how the galaxies are, because of how the stereographic projection works, anything that is on the surface of the hypersphere, when the interior is projected out, will remain on the surface. It doesn't get projected off the surface of the hypersphere. So when we reproject that matter which is outside of the surface back in, those galaxies remain on the surface.
So like centrifugal or transit shaping.
No, actually, that's it. That is interesting that you mentioned that. Someone else I was talking to tried to apply certain forces. And I guess there would be forces involved, but really it is about, it's kind of about dimensions and divisions of dimensions. So if something is at, it's kind of hard to describe it. Let's say a point is at 1, 0, 0, 0. So meaning that it's a point on the surface of the cube, of the inner cube. Then when that inner cube is rotated out, all of the stuff in the center of the cube gets stereographically projected to infinity, essentially, especially the closer it is to the 0 point. I think, how does that work? But anything on the surface of the cube that has 1, we'll get to, I don't know. I can't think of how to describe it, but should probably
it's
learn.
Like a geometric thing. It's a geometric thing.
Yeah, exactly. It's not complicated. I'm just not able to describe it properly. Sorry.
Like inside out geometry.
Yeah, right. So yeah, if you had a balloon and you have the space inside this, or like think about a rubber ball or something, and you cut a slit in the rubber ball so that you can turn it inside out. Well,
the balloon, actually you can squash it, and then
forget about the balloon because that's too messy. But let's say you have like a beach ball, but like quite a thick beach ball, and you cut it, or like a crappy plastic football, and then the space inside that football is a certain space. It has a certain shape. But if we cut the football open and invert the football so that shape inside inverts, so literally what was the central point of the football is now a point at infinity, and going back towards the football, then everything becomes smaller and smaller in a sense. Well, one thing that we notice is that the plastic of the football hasn't really gone anywhere. You know, all the space inside is expanded, but the ball is still the same size. So that's what I'm trying to say here, is that when we expanded all of the galaxies in the center to the outside to realize the way the universe is now with all of these galaxies around us, this hyperplane never changed, never moved, just inverted in a sense. And so when we invert the ball again, all the galaxies go back into the inside, but that, once again, the hyperplane remains in place. And what it appears to suggest, the position of the hyperplane, also suggests that these galaxies never move. So that ring of galaxies is totally stable within the, unless you're talking, if it's a sphere, it is a sphere of galaxies. So as all the other galaxies bunch up in one portion of the sky, like where the great attractor is, essentially, and then they move into the center in a straight line, they're going to punch a hole through this great wall. Now that's a bit strange because
like breaching the wall.
Well, maybe it won't. You know, maybe I've got it wrong, because if these invert, let me just think. Well, because we're talking about the football earlier, then that football does invert. Yeah, so I don't think that it wouldn't punch a hole, because all of these would also be inverted as they move back in. So their positions would alter and probably accommodate the motion of this galaxy in without any destruction. So the only destruction that's going to happen would be in terms of like the Milky Way, I suppose, will get obliterated.
Does it form like constellation because of that?
Oh, well, if I may add, everything out here, all of the galaxies in the universe, plus the Milky Way, are going to be, in their current state, would become kind of obliterated. So the only safe place really would be any of these galaxies and all of these ones.
There are only like 16 or 18 constellations or something, right? Something like that.
Oh, no, there's 88 constellations in the sky. Okay. There is 12 in the zodiac, which is the plane of the ecliptic, I think it's called. But constellations now, you have to remember, are effectively man-made, aren't they? We're joining the dots between the stars to say that looks a bit like an iron or whatever, you know.
Yeah, like yeah, we call it different names. Yes, Orion. Like,
you have constellations in India that are probably different to the ones we have, and then we're using the Greek constellations. Also, they didn't know about the constellations that were in the southern hemisphere, so we created a load of new ones like Triangulum and whatever down there. Scopus, I think, is another one.
Magellanic Cloud,
possibly, and also the Magellanic Cloud wouldn't be a constellation, because constellations don't consist of like one object. They have to be numerous objects joined up. And then the Chinese obviously have their own constellations, I imagine. They have their own zodiac as well. So, but yeah, that's a kind of a different issue, because I mean, you could join up a load of stars in the sky, and one of those stars could be reasonably close to the Earth, but another one could be like really, really far away. So the idea of that there's somehow a collection when they're all vastly different distances could be incorrect. But I just think from a maybe a science, cosmology, astrophysical point of view, that they're probably not that useful to describe anything. But I think maybe their constellations are probably more useful for navigation on one level, but also, you know, on a more kind of mystical sort of astrological level to do with
the North Star and all that. Yeah.
Well, yeah, I mean, the North Star is pretty interesting as well. So that's it. I'm glad I was able to show you something anyway, even though I couldn't find the quantum gravity research, and that quantum gravity research may be wrong.
Yeah, when you have that, when you can show that. But you had Gerd, where I didn't fully understand. We're going at it, and Gerd was kind of refuting yours. You are saying that that's not correct about something, the Earth being center or something. You know, the recent blog. You and Gerd were going at each other.
That was good. Yeah, I enjoyed that, because you know, I was more in my comfort zone. I was working from my theory. He's working from his. his research, and so we were able to
metric universe. Yeah.
Yeah, it was more of an equal contest than previous kind of all interactions with him. So so I thought that was good. Yeah, I mean, he is correct, but so what he's saying is that there's no central point in the universe, no geometrically special point. Every point is the same as the others. And whereas I was arguing that there are special geometric points from a four-dimensional perspective, and that we could talk about, you know, a point at z minus 1 and a point at z equals 1 and a point at z equals 0, which would be the actual canonical center of the universe from a 4D perspective. So these ideas are interesting, and basically what it hinges on is this issue that if you were to rotate the hypersphere that all of the galaxies are on, which is equivalent to just moving in any direction, like appreciable distance in any direction on the hypersphere or on the tangent plane, that will, let's say, we'll just think about it as rotating the hypersphere. Now the issue there is that there's a metric on the hypersphere that superposes, essentially constrains the sizes of things on the tangent space. So that metric has to be a particular, it has to get exponentially smaller as it goes up the map, up the hypersphere, so that when it projects out, all of the spaces are invariant. They're all the same, yeah? So if you move up the hypersphere and the metric doesn't move with the shifting of the sphere, then what's going to occur is that there will be a noticeable distortion of space, and the galaxies will be distorted. This is exactly the same as what the Lorentz contraction describes. As we head towards the speed of light, the celestial sphere gets distorted in terms of Lorentz transforms. So I think those are
the Doppler is connected with the Doppler effect also.
It's basically, no, actually, it looks a bit like a Doppler effect, but what it's saying is it's a Mobius transformation, right, of a sphere. So that's it. So there's some issue there. I mean, it might be more expedient if I were to look at that. If I were to look at the conversation, so I don't mess anything up, because these are kind of a little bit complicated. Yeah. So is the, oh my gosh, one sec. Oh, yeah, so you have the Mobius. So basically, when we've moved a certain distance on the hypersphere, if the metric doesn't move, then the projection will be distorted, and it will be obvious that there is an important geometric location in the universe. But if it does move, then there will be no obvious geometric point. So really, it's like if you were to go back and read Newton's Mathematica, Principia Mathematica, or whatever it was called. You know, at the start of that, he's talking about relative motion and the Earth, whether or not the Earth is static or moving, and the relative motion of the stars in the heaven, and the, you know, so this was a thing that they were dealing with at the time, and they couldn't figure it out. But wait a second, am I still sharing this window? All right, I'm not. So when they couldn't figure that out, but so we have this, but through time they feel like they figured it out. But what I'm saying is that we're kind of back to the same problem. We don't, if we were to travel very fast to a different location on the hypersphere, or just travel, or given enough time to get there, at whatever speed we travel, looking back at our position or just around us, would we see a distortion in the celestial sphere, or would it just look the same? In other words, I'm asking, does the metric move with the sphere, or does it stay in place? Or another way of asking it is, does the sphere stay in place and everyone has a unique tangent plane that moves up the sphere as it goes around? So these are the questions. We just don't know how to answer these questions.
I think it's had to do with linear time and non-linear time. I think
nothing to do with time.
No, because
there could be a time element involved. It seems to me that
because time, like I said, time and information are closely linked. So you have to have information travel in order to really, you are on the other side versus this side. You have to communicate somehow. So the information.
I'm not saying that time is like has no relevance to this. It's just it's less. I haven't really developed it that much yet. But well, this is one part. Like if we're talking about the magnetic monopole rays that take information from the hypersphere to the tangent plane, that's instantaneous. So, okay, but we'll move on from that. It seems to me that if we're talking about the metric gets smaller as it goes up to the top, so that it keeps spaces invariant on the tangent plane. They're all the same, because so. But there does appear to be an issue that as you move up the sphere, time gets faster. So at the point at infinity, then time would be moving.
It's superluminal, really.
It's hard to know because the metric at that point is 0. And at the speed of, if we were in a spacecraft traveling at the speed of light, the metric should be 0 there as well. So if you were traveling at the speed of light when you're at position z equals 1, meaning the zenith of the sphere, then you will be contracted to 0. The metric is 0. So it should look fine. Everything should be normal. So everything at the top of the sphere should travel at the speed of light. Although really it doesn't seem to work out that way. So there's a lot of stuff that needs to be done to see what is the truth of the matter, and also, you know, does this lead to a new understanding of relativity, or do we come to a point where we just say we honestly can't say? There's like too many options. Like, you know, if there's 2 options, then that's too many, because we can't say which one is correct. But
can you come up with the metric of the superluminal thing? Superluminal metric, can you come up with it?
I don't need to come up with a metric for the superluminal. You're talking about the monopoles, is it?
Yeah.
I don't feel it necessary to come up with one, but if you want to have a go, you're more than welcome. It's not really a metric issue there, because since everything is instantaneous, there's no need to discuss a metric. You could just have a point, couldn't you? You could just.
So you are saying monopole is instantaneous
transmission.
One side is monopole can be here, instantaneously can be on the other side.
Yeah, because it's a torsion field, right? It's rotating, and it's completely rigid in a sense. So whatever's
the short circuit,
whatever information is at the top of the monopole is transmitted to the bottom instantaneously through rotation. That's very simple.
I mean, you have a north monopole, south monopole. So it becomes, the north monopole becomes south monopole automatically, instantaneously.
Well, we don't really need to go into too many details, but let's say if we have the north side of the pole is when you're looking at, if you were looking at the projective point from the top, we see that, yeah, it's a rotational issue. So in fact, the whole pole is all spinning in the same direction, but it depends on which side you're looking at it, whether it becomes north or south.
It's about perspective.
Yeah, it's just a perspective issue, but this whole thing is about perspective. so there's also an issue with density. So as we go up the sphere, the metric is becoming more dense. Things are becoming smaller as they go up. So when they're projected, their density is probably decreased, but there could be a balance between the density as you go up and down. So what it looks like to me is that if it looks like relativity could be some kind of illusion. So special relativity I'm talking about. Because, okay, here's the point that we have to consider. In space, light travels in straight lines. But if we were to take a straight line from the tangent space and project it back onto the sphere, that's going to be curved. So on the sphere, all straight line paths are curved paths, which means that all light rays are curved on the sphere. And so those light rays, we would assume, because of the constancy of the speed of light, they're all traveling at c, yeah? But they're going through the metric. They pierce the metric as they go up to the zenith, yeah? Because they cannot circumpolar the zenith, because that would mean if the zenith is at infinity in our universe, and a light ray could circumpolar the zenith, like fairly close to it, that means that light ray would be traveling at an infinite speed around the universe in a circuit. So that's not possible. But as we, and it would, or it doesn't even matter if it was at the zenith or if it was really close to the Earth and traveling quite slowly. It would appear to us to be traveling in a circle, and light, as we know, doesn't do that. So that's just not possible. So all light rays on the surface of the sphere travel to the zenith, in a sense, but in a kind of spiderweb fashion, depending on where they're starting from on the sphere. So just let me think there. So the light ray pierces through the metric on the sphere, but if it's a constant speed, then that means if it's, let's say it's traveling 300,000 miles per second near the Earth with quite a large metric. As we go further out, the metric is smaller, but it's still traveling at that same speed. So when it's projected down, time in that area further away from us is happening much faster. So this is an interesting point. So time is happening faster there, but then as it arrives on Earth, it doesn't appear to be happening faster anymore because of a density issue, it's being stretched out. And there's some indication that when we look very far away, we can see events that we know take, like, let's say a couple of days. Some sort of supernova that has a standard candle kind of type 1a supernova, or yeah, that has a known lifespan. It's supposed to take a week to occur, but because it's further away, it takes 21 days. So we know, oh, there seems to be an expansion there of space. The light rays are being slowed. The event appears to be slower. So it seems to me that we need to, there's a contradiction there. If events are actually happening faster further away from us, why do they appear slower on Earth? But what could be occurring is that, think about it. You ever pour a pint of beer, or even like soda, but beer is probably better. And you see that the bubbles at the bottom and they're kind of flowing to the top, but because of the density of the water is more intense at the bottom than it is at the top, the bubbles are closer together because they have more water to push against.
The air is lighter than the water.
Yeah, of course.
They are air bubbles. They are air bubbles, right?
Right. Well, they could be nitrogen or something like that.
Yeah, but they are lighter. They are lighter than water. Sorry.
Yeah, of course. But like, let's say you're a bubble and you're forming on the bottom of the beer glass, and then you're trying to travel up to the top because you're lighter. But at the bottom, you have a lot of water to push against, so you're moving slower.
It's smaller. Also smaller. Then it starts expanding.
Right. Okay. So that's a good point. So then, as it goes up, it gets faster and faster because there's less to push against, and then, but at each moment in time, there's new bubbles on the bottom nucleating. But they're all nucleating. It's happening at a rate. So imagine we're on Earth and we have a light that's blinking on and off at a specific rate. And then far away on Arcturus, let's say, there's another light that's blinking at the same speed, I think. Right. But because time is happening faster right there, it's actually blinking faster. But then as the light ray approaches us, the metric expands. And so when it reaches us, it appears to be blinking at the same speed. Do you get me?
Yeah, I think also we have to consider that the bosons can interpenetrate each other. So that creates the instantaneity of light also. So that means that something is happening, that that boson there, or the light, somehow instantaneously gets here because of the interpenetration aspect. So this light becomes that light becomes the other light. Right?
Maybe, but there's another issue here that we have to discuss, which is like actual special relativity. So like if there was a spacecraft then flying by, now time is meant to be happening slower on the spacecraft if it's going up closer to the speed of light. But as we see, and the metric is supposed to be smaller. But what we notice is that when the metric is smaller, time is happening faster. So therefore, if we were to continue the analogy, time should be happening faster on the spacecraft than as it's moving at the speed of light. But we could imagine a sort of a gradient density. So like the metric is compressed in the spacecraft, but it's like a gradient decompression as it goes out towards the Earth, yeah, where we are stationary looking at the object. And that same decompression then decompresses the light that's coming from the craft, so that when we look at the craft, we see no time dilation, okay? Or, yeah, well, that's one idea. But let's imagine then that space-time is like the beer glass. We're low down in this density, and as the spacecraft goes up, it goes into a less dense area where time appears to be flowing slower. So the bubbles that are nucleating on the bottom of the glass are reaching the top at the same rate, but they're spread out. So that's it. So imagine what we're talking about is time nucleation. So imagine I'm here in Ireland and time is nucleating. You know, this is quite a difficult topic to discuss just randomly over you know,
exactly. I think also it is complicated by the linear time. I think I can explain from the linear aspect.
Well,
time and non-linear. Yeah.
Well, no. All right. Let's just get to the point here. So,
okay.
Let's say time in where you are is running normally. So you
can put a clock.
You have a clock ticking every second. Okay. Yeah. Now, right, and that clock is saying this moment is occurring now. You know, this event is happening now. But in my dimension or in my time, there's right. But oh no, wait. So you're further away, but your clock is ticking faster. Yeah. And then where I am, time is moving slower. But actually both events are happening at the same time. It's just that the events where I am are just nucleating like more slowly. So like let me think.
So information travel. The information travel is affected.
It's like it's a bit like if there was a movie where hang on a sec. It's just going to, the screen is blinding me. So,
also the difference between image and video, like
that's a good point. Like that's what I'm trying to get across. Is video is the answer to this. Like if I can explain this in terms of a video frame rate, that's going to that is what I'm trying to get to here. So imagine a frame from one image to the next, right? So each frame is an event, the space ticking, but the frame is nucleating slower. So, but somehow the two are identical. So far away, like the way the bubble is nucleating, the frames are happening faster, but as they get closer, they slow down to our rate. And the same is true in the opposite direction. So events nucleate here slower, but then as they travel out, they speed up. So the rate
may just become like video.
Wait. The rate at which the frames impact you, where you are further away, where time is running faster, the rate at which they come and impact you is the same rate that you experience time. So you would look at me and you would see that time is running the same speed here as it is where you are. But in fact, it's not. Time is running way slower here. So what we're talking about is that time is essentially quantized in a sense, you know? Either that or it's just...
The non-linear. Actually, I can explain from the non-linear and linear thing later on.
I seriously doubt it. That non-linear thing is...
No. See, where you are, for me, you are the non-linear time. I am the linear time. So when the non-linear time comes to me, it becomes linear, it becomes the same.
No, it's just way too, like this problem is complicated enough. Non-linear time is interesting, but...
Non-linear clock. You can think of a non-linear clock and a linear clock.
Yeah, non-linear clock, non-linear time. It's interesting, but the problem with it is linear time is nice because we can talk about one moment and then the next moment. The problem with non-linear time is that there's an infinite number of ways to permutate and arrange.
You can think of non-linear like exponential logarithmic time versus logarithmic or exponential time versus...
Yeah, you see, but there's so many ways you could look at it, you know? So I find non-linear time, I think, is interesting, but I think from a mathematics point of view, you know, it's another whole head-wrecking thing. So really what I'm saying is I might have some of the issues a bit backwards here, but let's say... Well, let's not turn relativity on its head and say that time is moving more slowly on the spacecraft, okay? So we're at the bottom of the glass, and this might be the more correct version. And then as the spacecraft moves out towards the speed of light, it goes into an area where space is less dense. In other words, it moves up to the top of the beer glass. And so from its perspective, the information that's arriving to it, like the bubbles that are nucleating on the bottom of the glass, appear to be moving more slowly, yeah? So from its perspective, time at the bottom of the glass, which is where we are on the Earth, essentially, that's the analogy I'm using, is moving slower. It appears to be moving slower. And likewise, but their time is also moving slower because they're less dense, yeah? So, but let's imagine that that's not the case. So we're looking at them and their time, their moments were nucleating back down to us. Maybe we would see that their time is slower. Oh no, this is it, sorry. Yeah, so this is it. So I think I'm giving you a general sense of what I'm talking about there, but imagine, have you ever seen those optical illusions where you see a color next to another color, and it looks way darker or way brighter. And right, so one color inside another color, and the two colors, and then in the other case it's reversed, with the first color is outside the other color or something. And the two colors look very different. One looks much darker than the other, but then when you isolate the two colors from their surroundings, you see that they are actually the same color. You know what I'm talking about?
Yeah. Another thing is,
wait, no, Rajan, I'm asking you a question there. You know
the color illusion. You are talking about color illusion.
Yeah, the color illusion, where it looks like they're two different colors, but they are actually the same color. You know,
because they are kind of merged together. It's like a super.
No, it's to do with the context of the colors. There's one called I think it's called the checker shadow illusion. I'll just share that with you, and you know instantly what I'm talking about.
Oh, it also has to do with resolution, because
no,
our eyes can resolve only certain.
Oh yeah, it could be to do with something like that. Let me think. Let's share this. Because yeah, I mean there could be all kind of ways to explain what's going on, but this is what I'm talking about. Yeah.
Okay.
Do you see this? This color A here is the same color as B, I think. Yeah, I think that's what they're saying.
Wait, because of illusion. Because of
the context. Because this color is surrounded by lighter areas, it looks darker. And because this color, which is the same as A, is surrounded by darker areas, it looks brighter.
So if you move that, what about the prism? What you call the cylinder?
Yeah.
If we move it near A, it'll flip. So A will look bright, lighter, and B will look darker if we move the cylinder.
Technically, yes. Yeah, because the shadow is the thing that's making this gray cube here darker. So what you notice is that this. So that's basically what I'm saying. It's to do with context, yeah. So what I'm saying is that when the spacecraft is flying at a high speed and its time is running slower, it's an illusion that the data is running slower. It's just because we're comparing it with the background, essentially. In the background, everything is, the speed is normal, and the time around us is running normally. So when we compare it to that, it looks slower, but it's not actually. So, but if that's the case, and time is running normally on the spacecraft, then what accounts for the time dilation that we see in particle accelerators and stuff? Yeah. So this is a big point that we're trying to get to, like this resolution of the paradox that Christian was talking about as well, to do with his, you know, he has a quantized time of 1/6961, I think it is. So
yeah.
So this is it. So my thinking is that, and this has to be shown in the papers that I was talking about earlier with the particle accelerator experiments and silver ions. As the craft is going out, time is slowing down for it because it's speeding up. But as it comes back, or as it slows down, time speeds up again.
Yeah,
right?
So it kind of balances out.
Yes, exactly. So that's why the time on the spacecraft appears to be slower, but it actually isn't. It will just, all of the moments will just catch back up to it. So it is exactly like a Doppler effect, which is an illusion anyway, right? Because if I'm sitting here and I hear an ambulance siren, and it sounds like the siren is going up in pitch as it comes close, and then down in pitch as it goes away. But the people on board, they don't notice any pitch change. Yeah. Right. So that's the exact same thing with the time. It's an apparent illusion. As they move away, time goes slower, and as they speed up, time goes slower. As they slow down, time speeds up. So the balance between the slowing down and the speeding up cancel out, and then the time is just the same.
Yeah,
which
that's fantastic. Yeah.
So
we can kind of wrap up in another 5 minutes, probably.
Yeah, so that's what I'll have to look into in the papers to see. Right, fine, they've accelerated these particles, and they've measured the time slowing down. But do they ever measure the time of the particles as they slow down within the collider? You know, do they notice that the ticking starts increasing as it slows down by the rate necessary to cancel out the time dilation effects that they observed in the first place?
The muon experiment also maybe been similar. Possibly.
Yeah, except that's a decay thing, so that mightn't be that useful because you cannot recover.
It's a directional thing. It's a directional thing.
Well, if it's the muon decay, then you can't recover the muon because it's gone. But with the
reversible thing, you need a reversible react.
Well, but even with the atomic clock, it's a cyclical thing, so it doesn't matter. So yeah, it'd be interesting to see if they do those kind of experiments, or if they've accounted for that. And if they have, then what I'm saying is, obviously not right, and I'm just wasting your time. Oh yeah. So anyway, Rajan, nice to talk to you. I think we'll leave it there.
Yeah, we'll see next week. Very interesting things we talked about. So we will continue. Some of it I think have potential thing to explain the thing about. I feel now about asymmetry of field, about magnetic and electric. If we can explain it with your theory or with the other things, I think we can explain most of the other things. I think, even including that.
Yeah, it might be a bit too simple to explain everything, but it's interesting.
It will give a good base to explain, to understand that what.
I think it's good to know. It's good to block it off anyway, because it probably wouldn't take you too long, and if you just go down that road and see what are the logical entails of this concept of a symmetry between the electron and magnetic electric fields in the Maxwell thing, and then see, like, is there a possible asymmetry here? And if not, then at least there's no point in looking down that road.
Because
but if you do find something, then fantastic. Yeah. Okay.
Like what Christian is saying, Christian is saying about the constants, the permittivity and the permeability are different. So that itself is a asymmetry. So, and then you have the rho versus the other aspect, the flux. Those kinds of things. We look at that. We might be able to see where the asymmetry, if it is there, will come from. We'll see.
Okay. Okay. Well, yeah. Chat to you later.
Talk to you. Have a nice week. Thank you. Thank you.
I'm gonna end the stream there then.